Title is Top Eigenvalue of a Random Matrix, a Tale of Tales. So the Subramaniam Chandrasekhar lectures are a very important part of the ICTS programs, in the sense that they invite distinguished scientists to speak about their work. The first lecture is a colloquium level lecture. The rest are, the other two lectures in the series are more technical. And there is usually a workshop around the theme of these lectures. So fortunately, this time, we not only have a conference around the theme of these lectures, but also there was a school preceding this conference. So it gives me great pleasure to introduce Satya Majumdar. He was a student at the Tata Institute from where I am. And he graduated in 1992. I think he's two of the best students that TIFR has produced in the physics department in the past several decades. After his PhD, he went to the United States for his postdoctoral work, I think with Subir Sachdev, and I think then he came back to the Tata Institute as a faculty member, and then was taken away by the love of Paris to France. So, in France, Satya is Directeur de Recherche in CNRS. It's a laboratory de physique théorique sorry, my French is very bad, for statistical modeling of the University of Paris in Orsay. He's also an adjunct professor at the ICTS of TIFR and the Department of Theoretical Physics of TIFR. He's a very anointed person. He received the Paul Langevin Medal for Theoretical Physics from the French Physical Society in 2005. And he is one of the leaders in the area of statistical mechanics. His contributions are very broad and wide-ranged. Problems in equilibrium and non-equilibrium statistical physics, with applications ranging from granular systems all the way to analysis of algorithms in computer science. His most recent work has to do with applications of statistical physics in computer science and extreme value statistics in various systems, and in particular to the theory of random matrices and its various applications. And I think there is even a distribution named after him, which is called the Majumdar-Vargasola distribution. Okay, so with these few words, I'd like to invite Professor T.V. Ramakrishnan to say a few words and then give a memento to Satya on this occasion. Professor Ramakrishnan.
Spenta said, which is that it's also a matter of special personal pleasure for me to be here and to listen to Satya Majumdar talking, partly because we knew each other when both of us were much younger. And it is so good to see someone do so well and to learn about new things. And especially to see someone who has pioneered the exploration of hard mathematical truths beyond random things. His PhD was on, as Spenta almost said, was on self-organized criticality in sandpile models with Deepak Dhar. And I met him, I think, for the first time in Bell Labs when he was working on transport in vortex liquids. He has the span of what he has done is enormous, as you can guess from that and from what he's going to say today. And actually, it is particularly appropriate that he's talking about such a thing today as a Chandrasekhar Memorial Lecture, because Chandrasekhar himself, for a reasonable length of his life, between 1938 and 1943, very deeply involved in Brownian motion. And he has written a very famous review article in the Reviews of Modern Physics on, I think it is called Stochastic Processes in Physics and Astronomy or some such thing, because he was interested in how these processes affect radiative equilibrium in stellar atmospheres and stellar dynamics. So without saying much more, I would like to welcome Professor Satya Majumdar to the dais, and I'm supposed to give him a bouquet of something.
Come on.
Thank you, Professor Spenta Wadia and Professor T.V. Ramakrishnan for this kind introduction. And also, it's a great honor and pleasure for me to give this series of lectures, Chandrasekhar lectures, and to this distinguished audience. And also, this last school and the conference has been really fantastic. And I would like to thank all the organizers like Abhishek, Sanjeev, Rajesh, Justin, Govind, and Manju. So for the hard work they have put in. So it's really great pleasure to be here. Okay, so today I'm going to talk about top eigenvalue of a random matrix, but this is a talk which is meant to be for general audience. I should start with a brief historical remark before I actually get into the body of the talk. And the talk is aimed at sort of general audience. So it might be a little bit of repetition from my random matrix friends, so they might get bored. So please excuse me for that. Okay, so basically random matrix theory, so historical remarks, is that it basically goes back to 1928 in a paper by John Wishart, who was a statistician, and this was published in this journal Biometrica. And basically what Wishart was interested in is what I wrote down here. It's a very simple thing, essentially. So this is, imagine that you have a class and there are students. Let's say you have 3 students, okay, and there are physics and maths course, and these are just the exam marks, some numbers basically. Okay, so you have your empirical sample. This is a sample you have. In general, it will be m by n, a rectangular matrix, and suppose you want to know what is the correlation between the physics and maths course. If a student is good in physics, is she or he is going to be equally good in maths. So in order to understand the correlations inbuilt in this object, so what one does is to take this matrix, if I call X matrix, and you just transpose it and multiply it by X, call it W. So what is this W matrix? So this is called the covariance matrix. What are the elements? You just do it this 2 by 2, 3 by 2 case. So this is going to be 2 by 2 matrix because its transpose is 2 cross 3 and this is 3 cross 2. And what are the elements? So the elements are here. So look at the first element here. So this is x1 squared plus x2 squared plus x3 squared. What is that? So if I divide, if I divide by all of them by 3, just a number, and multiply just outside by 3. So then you see this is just, imagine that this is 0 mean. So this is just the variance of the physics course between the students, and this is just the variance of the maths course between the students. And what is this object here, the off-diagonal element? So this is nothing but the correlation between the physics and maths course. x11, x12 plus x21 plus x22 plus x31, x33. Okay. So this is called the covariance matrix, and the elements of this matrix tells you how much fluctuations are there or correlations are there between the physics and maths courses basically. So this is what is called the Wishart matrix, and I'll come back to that later in the talk. And so Wishart was interested in this, and his thing was that imagine that the underlying score is completely random. Each of them are random objects taken from something, some distribution, and then that induces a distribution on the elements of this covariance matrix, and he was interested in knowing the fluctuations of this. And this is viewed as a kind of null model, because you don't know what the underlying distributions are, but you want to compare it to something. So one of the ways to do that is to assume that they are random, and sometimes even when the data is large, random is a good approximation. And so basically the eigenvalues of this matrix will tell me, what are the fluctuations. So there might be one very big eigenvalue, which will mean very strong correlation between the physics and math scores. And so this is in fact the heart of what is called the principal component analysis, which is routinely used in many practical applications like image processing and computer vision and so on. So this has played an enormous important role, and this was the first time random matrix theory was introduced into the scientific literature. And then, as you all have heard, that Wigner actually introduced it in the physics literature. And so this was a conference on neutron spectroscopy in which there was a chairman whose name was W. Havens Jr. And so they were looking at the neutron resonance level spacing distribution here. And so they asked Wigner that how did you think of this? And so here is what Wigner replied. Where does one find out about Wishart? He said, I came to know about this from the Wishart distribution. So this guy asked him that where does one find out about Wishart distribution? So he says the Wishart distribution is given in S.S. Wilkes' book about statistics, and I found it just by accident. Okay. So this is how the random matrix theory came. So what was Wigner's motivation for it? Basically, if you take any heavy nuclei, okay, with lots of protons and neutrons, like uranium-238 or thorium-232, and if you look at their energy levels, of course, it's a very complex Hamiltonian with lots of interactions between different elements. So you can't possibly hope to solve completely the the eigenvalues of this complex Hamiltonian. But if you look at their spacing distributions like this, so then you see that there is some kind of universality between these two. They look kind of similar, and so Wigner's basically intuition was that basically, okay, I cannot solve this complex Hamiltonian. What I can do, that there must be some statistical description which is universal. And so he said, okay, replace this complex Hamiltonian by some random matrix which satisfies some basic symmetries of this Hamiltonian, and otherwise all the elements are random. And that is how the random matrix theory came into the nuclear physics literature, and it was extremely successful in explaining many of the nuclear physics features, which I won't go into the details. And then the mathematical theory of random matrix was of course developed by Dyson, Godin, and Mehta, beautiful techniques of orthogonal polynomials and so on. And the subject has been there since 1950s essentially, and it kept appearing in many different contexts. And here is a list of things, which is not exhaustive, but you can see that how many different areas this random matrix theory has made impact. So physics is nuclear physics, quantum chaos, QCD, cosmology, string theory, statistical physics. In mathematics, zeta function that you have heard from Professor Keating's lecture, free probability theory, combinatorics, knot theory, integrable systems. In statistics, of course, it has played very important role in image processing, data compression, information theory, wireless communications. The cell phones that you're using actually use random matrix theory. And then in biology, RNA folding, sequence matching will hear. And this conference was sort of meant to bring together many people from different backgrounds and to have a common sort of language of because all of them are using essentially the random matrix tool, and that was basically the idea of this school and the conference. And so you can see that it has really exploded in some sense in so many different areas across the fields, not just physics and mathematics, but many other things, economics and finance also. And here is some recent references where many people actually have contributed, and you can find some latest applications of random matrix theory. So with this sort of brief introduction of random matrix theory, I'm now going to the main body of my talk, where I'm going to talk about the largest eigenvalue of a random matrix. And the reason, so here is the plan of my talk. So why are you interested in largest eigenvalue of a Gaussian, let's say Gaussian or any random matrix? There's a general motivation, because if you take any system, quantum or classical, basically you have the energy levels of the system, and if you are in low temperature, then low temperature properties of the system are governed by the ground state energy and its fluctuations. So for example, if you are in a disordered system like spin glass or polymer random medium, then basically the ground state energy fluctuates from one sample of disorder to another sample, and you want to know really how does the ground state energy fluctuate, what's the distribution of the ground state energy. So that's a sort of very generic motivation. And so why random matrix? Because in most of the realistic systems, the energy levels are actually strongly correlated. They are not completely independent. If they were independent, then the theory would be very simple and classical extreme value statistics. But they are extremely strongly correlated, and so random matrix theory actually provides a very simple sort of useful toy laboratory for studying strongly correlated extreme value statistics of strongly correlated systems. And so that's sort of very general motivation, but I'll come to specific things later. And so it has this lambda max of the largest eigenvalue has been studied in detail in many of the works. I'll go through some of them, and what I'll show you in this walk, I'll talk in the end it's actually going to be a very, very simple problem of a Coulomb gas, a classical Coulomb gas. You can forget about random matrix. It's a classical Coulomb gas with a wall essentially. I'll explain that. And there is this famous limiting distribution called the Tracy-Widom distributions that many of you heard many times in this conference, but I'll tell here a little bit more detail. This Tracy-Widom distribution they discovered in 1994, which is the distribution of the limiting distribution of the lambda max for Gaussian random matrices, and then it has been found to be universal in many other random matrix ensembles. And there's an explosion of work both in physics, statistical physics literature, as well as mathematics probability theory literature. And it's like the Gaussian distribution and central limit theorem. The Tracy-Widom distribution has been found in many different problems. And so there is a lot of activity around that, and you have heard many of them in this conference. And what I'll focus on today is not just the limiting distribution, which happens when this matrix is very large, but I'll also talk about something called large deviation tails, and which is not included in the Tracy-Widom. And we'll see that the left and right tail, I'll explain to this in more detail later, it actually corresponds to something like a pushed Coulomb gas, and right tail is like unpushed Coulomb gas or pulled Coulomb gas. I'll explain these things. And what you discover here, that there is a third order phase transition between the pushed and the unpushed Coulomb gas, okay, which is actually inherent in the distribution of the lambda max, okay. And it turns out that this third order phase transition, which is associated with this Tracy-Widom and the left and right tail of the large deviation tails, it's exactly in the same universality class as the third order phase transition that one found long back in 2D large N gauge theory. In fact, the lattice version of UN lattice gauge theory is called the Gross-Witt and Warrior transition. I'm quite happy that Spenta Warrior is present here. And the continuum version is called the Darhus-Ulsen or Douglas-Kazakov transition. So it actually turns out to be exactly in the same universality class as this long, that sort of makes a nice connection between the two fields. And in fact, what we have found last few years of work is that this third order phase transition actually pops up in many different places. It's a kind of ubiquitous object, including in the distribution of the conductance that Kedar Damle talked about this morning. And it appears in many different places, and I'll discuss some of them as I go along. And so this is the sort of main message of my talk, that there is a third order phase transition which is ubiquitous. So if I can't finish in time, this is the main message basically. And then I'll talk about extension to Wishart matrices. This is Gaussian matrices I was talking about here. Sorry. And so Wishart matrices, and there are some recent experiments which I hope to talk about, which is in a coupled fiber laser, it's optical system done at the Weizmann Institute in the group of Neil Davidson, which can actually measure not just the Tracy-Widom distribution for the Wishart matrices, but also these large deviation tails. And so this is a very nice experiment, and I'll talk about that, and then finally I'll summarize and conclude. So that's the program of the talk, and I have how much time exactly, Rajesh? 50 minutes? Okay, good. You just tell me, stop me whenever you, okay. All right, so let me just start with a trivial problem, okay. So all of you know, even a high school student can do this. So imagine that you have just a diagonal matrix, okay, just 0, 0, and this is the diagonal elements. And imagine that this diagonal element, each of the elements, they are independent, and each of them is drawn from a Gaussian distribution, okay, very simple. So you have n eigenvalues, and trivially, all the eigenvalues are exactly equal to the matrix elements themselves, because it's already diagonal. okay, and they are independent. And suppose I ask this question that what is the probability that all the eigenvalues are negative? Okay, I'll come to that in a minute. Just ask what's the probability of all these. So this is trivial to answer because it's like a coin tossing. So each coin can be either up or down with probability half and half. So therefore it will be just, and they are independent, so it will be just 2 to the power minus n. So as n increases, it decreases exponentially this object, this probability, with a coefficient here which is log 2. Okay, so this is a trivial problem. Now let's ask the same question for now not just a diagonal matrix, but you have a real symmetric matrix. So I take a matrix and these elements are real and symmetric. Okay, and again I do the same thing, that I choose all the matrix elements from a Gaussian distribution independently, and so basically you can write down the joint distribution of the matrix elements as exponential minus half trace of x square. So this is what is called the Gaussian orthogonal ensemble, because the measure, the probability is invariant under a rotation of this x. So this is the the classical Gaussian orthogonal ensemble. Okay, so basically think of it as a real symmetric matrix. So therefore all the eigenvalues are real, so there are n eigenvalues. And the point is that unlike in the previous example, these eigenvalues are strongly correlated. And so now if you ask the same question, that what is the probability that all the eigenvalues are negative, which is the same thing as asking what's the probability that the largest eigenvalue is negative. Okay? So this turns out to be, of course, much more non-trivial compared to the previous trivial case where it was completely diagonal. And the reason is because these lambdas are very strongly correlated, as we'll see. And it turns out just this problem, this is a very well-defined problem. You can tell it to any graduate student. And this problem is actually appeared in many different contexts in both physics and mathematics literature. To my knowledge, it first appeared in a classical paper of Robert May in Nature in 1972 in the context of ecosystems, where he was interested in the stability of a large ecosystem. And basically he came to this question. He could not solve it. And and he in fact was sort of referring to some kind of phase transitions in the system. I'll come to the phase transition a little bit later. And this is the ecosystem, okay? And then later Cavagna et al. And also Fyodorov and Williams and many others in glassy systems. This is and I'll elaborate on that a little bit later. The same question appears. It also appears in string theory, on the landscape-based string theory, where in this paper by Susskind and then Douglas and many others. And also in mathematics, in random polynomials, random words, and all these things. So this is a sort of very central problem which appears in many different areas. And the question is, what is Pn? We saw that for the completely trivial case, it decays exponentially as e to the power minus n log 2 or 2 to the power minus n. So you ask, okay, in this case, how does it decay? Okay, with n. So what is known about this? What can you say? So you're asking this question. So I have a real symmetric matrix, and I want to calculate what is the probability that all the eigenvalues are negative. So what's the probability matrix is negative, basically. Okay. So n equal to 1 is trivial because you have one element. So what's the probability that the the eigenvalue of the matrix element itself is negative? It's half trivially. Okay. N equal to 2, you can do a little bit of work. You just have to diagonalize, and this is a trivial, not so difficult. You find 2 minus root 2 over 4, which is less than 0.5. N equal to 3 turns out to be already quite non-trivial. And in fact, it was sort of worked out in these two papers recently in 2007. So this is pi minus 2 root 2 by 4 pi. So it actually decreases quite a bit. So it's decreasing with n. Okay? And you want to know how does it decrease for large n. Okay? That's the question you want asking. How does Pn decay for large n? And so it's so these gentlemen, Azami and Esther, were actually cosmologists from Yale University. So they were studying this problem numerically. And what they predicted is that for large n, it actually should decay like exponential minus some constant times n squared. And they found numerically this constant was 0.27 roughly. Okay? So it's actually much faster than the trivial case that I discussed where the matrix was completely diagonal, where it is decaying exponentially. Here it's decaying as exponential minus n squared to leading order in large n. Okay? So it's a very small probability. So it's a rare event. So that means this event that all the eigenvalues are negative is a very rare event. And so in collaboration with my colleague David Dean, so we actually, in 2006, we actually computed this number exactly. And it turns out to be 1/4 times log 3, and I'll explain to that in a minute. So this is the exact value. And then it turns out that, of course, this was for the Gaussian orthogonal ensemble. But you can also ask for other ensembles like Gaussian unitary or symplectic. I mean, basically what happens is that this beta, which the Dyson index, which describes the ensemble, just comes out as a front number, but this theta doesn't change with the different ensembles. Okay. So now why one is interested in this problem? Why is it this problem interesting? Okay. So now I come to the main motivation of this. I mean, it's one of the motivations, but as I showed you, it appeared in many different contexts. This problem. So here is one simple motivation. Okay. So imagine that you have a particle moving in an n-dimensional landscape. So landscape is some potential v, y1, y2, y3, yn. These coordinates is just this is the n-dimensional landscape. So in spin glasses, this is just the free energy landscape. In structural gases, these coordinates y1, y2, y3, yn, they are just just denote the label the configurations. So you have different configurations, and you have a potential free energy landscape basically, in which a particle is moving just by just steepest descent dynamics at 0 temperature, let's say. In the case of string theory, this is just a moduli space, and a minimum of this landscape would correspond to our universe and things like that. So basically what we're looking at then, so because of this dynamics, so clearly the particle will get stuck whenever you have a stationary point. Okay, so grad v equal to 0. That's maximum or minimum or saddle point of these things at some stationary point y star. And so near a stationary point, you can expand your potential. So you can write down this. So first derivative term, of course, will be 0 because grad v is 0. So the only non-zero term, first non-zero term will be the second derivative. So this is yi minus yi star, yg minus yg star, and the coefficients here is just the Hessian matrix evaluated at the stationary point. Okay. So this Hessian matrix, of course, plays a very important role in glasses and supercooled liquids and many other problems. And so this is clearly a symmetric matrix, and the eigenvalues of this matrix determines the nature of the stationary state. Is it a local minimum, is it a local maximum, or is it a saddle point? Okay. So for example, if you have a one-dimensional surface, the Hessian matrix is just a del 2v del y square second derivative, and we all know that if the second derivative is negative, you have a local maximum, and if the second derivative is positive, you have a local minimum. Okay. When you go to two-dimensional surface, so Hessian matrix is a 2 by 2 matrix, symmetric matrix, and so we know what we know. If there are two real eigenvalues, lambda 1 and lambda 2, so if both are negative, you have a local maximum. If both are positive, you have a local minimum, and if one of them is negative and one of them is positive, you have a saddle point, like this example here. So in this direction, as you go from here to here, it's a negative, and this direction is positive. So this is a saddle point. Okay. So now comes the main thing, that imagine that you have a n-dimensional landscape, and you have a Hessian matrix H, and in this so-called random Hessian model, what people model is that this is a n cross n real symmetric matrix. Now obviously, and the simplest assumption is that they are just taken from a Gaussian orthogonal ensemble essentially. Now this is of course not a realistic model of any glasses or supercooled liquids and so on, because in most cases, if V is for example some Gaussian random field, then essentially these entries of this Hessian matrix are very strongly correlated. So you cannot assume that the entries are independent. However, it turns out that this same problem, essentially comes as a intermediate step. I will not discuss on those details. This is work of Fyodorov and Williams, where they have shown that basically if you can solve this problem, you can actually solve essentially the realistic problem of Gaussian random fields. And plus, of course, in string theory context and also in the ecology context, this problem essentially this problem which appears. Okay, so this is the problem we want to go to study. Okay, so basically, within this context of random Hessian model, so Pn is the probability that all the eigenvalues are negative, is just the fraction of local maximum or local minimum. Because it's a Gaussian ensemble, so there is a lambda going to minus lambda symmetry, which means that number of local maximum will be same as number of local minimum. So fraction of local maximum or local minimum is this object Pn. So basically, what we see is that the probability that the largest eigenvalue is negative, okay, which is the same event as this, is just counts the fraction of local maximum or local minimum. And the result that it decays, it's very, very small, very tiny, okay, e to the power minus theta n square, which indicates that most of the stationary points within this random Hessian model are actually saddle points, because the fraction of local maximum and local minimum are very, very small. So most of the stationary points are actually saddle points. Okay. So, okay, all right. So now I'm going to just remind you a little bit of just a basic intro. So we want to study this P of n, and we want to know how does it behave for large n. But what I want to show you is that this question is not just restricted to this. It's actually part of a much more general function, and that is what the main result of my talk would be. So now I'm going to just remind you a little bit about the basics of random matrix theory for those of you who are not familiar with. So if you have an n cross n Gaussian random matrix, then as you have heard from many talks here, there are these main three Wigner Dyson ensembles, namely that the orthogonal, unitary, and symplectic, and which means that the entries of this matrix are drawn from some joint distribution. They are independent, and they are drawn from some joint distribution of the elements, which is trace of the inner product of x and x. So for real symmetry, which is orthogonal, is just trace of x squared. For the unitary case, where the matrix is actually complex Hermitian, so this is x dagger x, and symplectic is a little bit, it's a self-dual. Okay? And these are usually, denoted by this number, which is called the Dyson index, where beta equal to 1 means, and I'll explain to that a little bit, is GOE and GUE and GSE. And I actually put a factor of n outside here, so that the eigenvalues are of all order 1. Okay. So this is the statement of the problem, and now you just diagonalize your matrix, and you ask, okay, so eigenvalues are also going to be random because my entries are random. So clearly, so you can ask what is the joint distribution of the eigenvalues. And it so happens that for this ensemble, you can actually write down the exact joint distribution of the eigenvalues. You can actually, they factorize from the eigenvectors, and you can integrate out the eigenvectors, and you can just write down the joint distribution of eigenvalues. So this is well known. I don't know if it was originally due to Wigner. Maybe it was even before that. This is a classic result that all of us know. So this is basically, so there is a factor here, which is precisely this object. When you trace of x squared, is just summation lambda I squared. But there is an additional factor which comes in, which is due to the Jacobian of the transformation from entries to eigenvalues, and this Jacobian is what is very important. And the back factor beta here says that the Jacobian strength of the interaction between the eigenvalues, and this is the classic level repulsion, because it says that probability that two eigenvalues are next to come very close to each other is going to be 0. Okay, so beta equal to 1, 2, 4. These are the three classical ensembles, so they denote the strength of the eigenvalues. But we have heard from Balin-Thirad's talk that although originally Gaussian ensembles were for beta equal to 1 and 2 and 3, but later on there were other matrices which are found, like tridiagonal matrices with some special entries, which also gives rise to this generalized beta ensemble with arbitrary values of beta. So we're going to study for arbitrary values of beta here. Okay. So this is the key result. So once you have that, you can actually forget about the matrix, and you just want to look at this object. Okay, this joint. This is the key result, and there is a prefactor here, which is just Zn, which is called the partition function of this matrix model, which is exponential minus beta by 2n summation lambda I square plus this. So notice that if I did not have this factor here, then all the eigenvalues are completely uncorrelated from each other, because the product is just a joint distribution is just a product, so it's completely independent. In that case, if I'm interested in the largest eigenvalue, that will be classical, Gumbel statistics or something. Never, if you don't know, but it's very simple basically. However, it's the correlation between the eigenvalues, which is this repulsion. So this is what correlates the eigenvalues. That is what gives rise to the non-trivial results for this random matrix problems. Okay, so this is a strong correlation that I was talking about before. Okay, so we have this. So what can we say from this? So, okay. So we have this partition function. Okay, so this is beautiful, because now what I can think of this is the following. So I can write down this van der Waals as exponential minus beta over 2 times log of lambda j minus lambda k. So once you have this representation, then it's actually quite nice, because this, what does it? So you can actually just interpret this. Forget that these are eigenvalues of a matrix. You can think of this lambda as positions of some charged particles on a line. Okay, and these particles, they are repelling each other by a logarithmic interaction. Okay, so the logarithmically repel. So it's like a Coulomb gas. However, it's not quite Coulomb gas, because Coulomb gas logarithmic interaction happens in 2 dimensions. Here, these objects are actually restricted to 1-dimensional line, so it's not really Coulomb interaction, but it's a log of lambda j minus lambda k. So they're repelling each other. Okay, but they're also sitting in an external confining potential, which is a quadratic potential for the Gaussian case. In general, for arbitrary matrix model, it will be some other potential v of lambda. Okay, so what is the effect of these two? So basically, there are two competing terms. So these guys which repel each other, so they're trying to put the charges apart from each other. Okay, whereas this guy is trying to push them towards the origin. Okay, so as a result of the competition between these two terms, the system will settle down into some compact object around the origin, and we'll see what it does. Okay, but first let's see what is the typical value of an eigenvalue. Okay, So how do I estimate the typical value? It's just the balance of energies. We have two energies, the attractive energy and this repulsive energy. So essentially, so first term goes like n. I put a factor n there. So essentially, you will have n square, because there is sum over 1 to n. So there will be n square terms times lambda square. So that's the order of energy of this attractive energy potential. And here you have pairwise energy. So you have n into n minus 1 over 2, which is of order n square. So basically what you see is that a typical lambda is going to be of order 1. Okay? So basically what we have here is a classical Coulomb gas of particles in an external confining potential and logarithmic repulsion. So this is what I want to study now. So I can forget about my original random matrix, and we are now in the domain of classical statistical mechanics, which is very nice. Okay, very simple. All right. So what do we know about this? So I have this gas. So as a result, as I said, that because of this competing interactions, the system will settle down into some kind of equilibrium state, and which is just, so this, you can interpret this as the Boltzmann weight. So this is just the partition function, normal. So first thing to ask is that when n goes to infinity, that is when n is large, basically these eigenvalues, okay, I can remove this. So when the n is going to be large, they are of order 1, but right here, and of these eigenvalues basically. So density is just this object here, which is the delta function. It's just a counting function. It counts how many eigenvalues are there between lambda and lambda plus d lambda, what fraction of eigenvalues are there, normalized to 1. Okay, and this is the classical result. In the large n limit, this object tends to this Wigner semicircular form. So which means that there are lots of eigenvalues near the center, and then their density decreases as a square root singularity here, a square root singularity, and it vanishes at the two ends, minus root 2 and plus root 2. So beyond that, on an average, there are no eigenvalues. Okay, so this is the Wigner classic result of Wigner semicircle law that all of you have probably heard about, and inside is called the Wigner C. Okay, so once you have that, now we are interested in the largest eigenvalue. That means you have this object. So I'm interested in this guy over here, the top eigenvalue. Okay, because that's what I want to compute. And so what we see from this classical result, without doing any computation, is that the average value of lambda max is square root of, this is the average, right? This is the average density. So on an average, the lambda max is square root of 2. Okay, but however, it will fluctuate, of course, from one sample to another sample. So if you do one experiment, you will find here. If you do another experiment, you might find the eigenvalues like this. So it fluctuates from one sample to another sample, and you want to know how does it fluctuate from one sample to another sample. So there will be distribution around the square root of t2, and you want to know what is the distribution. Okay. So here is the Wigner semicircle again. So as I said, lambda max is going to fluctuate from one relation to another relation. So this is a schematic picture of the probability density or probability distribution of this lambda max, for example. Okay, so you know that it will have a sort of peak around its average, and basically there is a typical fluctuation. So typically it will fluctuate from one sample to another sample, and the typical fluctuations is of order n to the power minus 2/3. This is very easy to guess, because how do I guess the typical fluctuations? Because so if you have the Wigner semicircle here, so here at the edge, which is A, so the density is actually going like let's say a minus lambda to the power, in general, some alpha. So in our case, alpha equal to half. So if I want to find out that what fraction of eigenvalues are there between this t and a is the age of the support. Okay, so what fraction of eigenvalues are there between t and a? So you just have to integrate from t to a this rho lambda d lambda. Okay, so when t is very close to a, this goes like a minus lambda to the power alpha plus 1. Okay. Now if I put this t to be the largest eigenvalue itself, lambda max, okay, and so I'm saying that this is my largest eigenvalue. That means all the eigenvalues are to the left of that, and then I'm asking what fraction of guys are there in this interval between lambda max and the edge. So this clearly is going to be only one of them, right? Because lambda max is just here. After that, there is nothing. So it's basically, this object is going to be 1 over n. Fraction of eigenvalues which are there between lambda max itself. So as long, if I put this to be, sorry, this is t. So if I put t to be lambda max, okay. So then you just have one eigenvalue, so the fraction is going to be 1 over n. As a result, so from this you can estimate that lambda max minus a should go like n to the power minus 1 over alpha plus 1 typically. Okay, so alpha in our case is half, so which means this will go like n to the power minus 2/3. All right. So it's actually very small, very tiny fluctuation. So that means when n is large, it hardly fluctuates from its average value. Okay, so it's very close to √2, and so you can ask, okay, if it is of this small, but so I can go and zoom in this part, and I look at what is the sort of limiting distribution. If I scale by this object, then that is the famous Tracy-Widom distribution. So here I'm looking at the cumulative distribution. So this is the PDF, if you like. And if I plot the cumulative distribution, that is what's the probability that lambda max is less than or equal to some number w, then as w goes to infinity, it should go to 1 because it's the integral of this curve up to infinity. So total probability is 1, so it goes to 1, and it goes to 0 as w goes to 0. So here is this blue regime here around the √2. Okay, so this part is a width of order n to the power minus 2/3, and what Recherche and Widom showed is that if you go zoom in into this regime, and basically, so you have a w minus √2, so you have to take w to be very close to √2 and n to be large, but keeping this product fixed. Then this actually converges to a unique scaling function f beta, and this which depends on this index beta of which Gaussian ensemble you are talking about, and this is this famous Tracy-Widom distribution. And once you have that, the probability density, the PDF is just the derivative of this curve. Okay, so they computed this object here. And basically, what is this function looks like? So this turns out to be related to some solution of Painlevé-2 equation. So if you don't know what is Painlevé-2, don't bother. I mean, I'll just just flash some mathematical formulas, but it's not that you have to understand the details of it, but just for completeness. So basically, so this function, scaling function f beta x, so it's actually it's written in this way. It involves some function q of y, and it's integral of some function of q of y, and this q of y satisfies the second order nonlinear equation, which is called the Painlevé equation, with a prescribed boundary condition. Okay, don't bother about the details if you can't follow it. So this goes like airy function. So once you specify this boundary condition, there is a unique solution called the Hastings-MacLeod solution. And so once you have the solution q of y, you just calculate that and you plug it in here. Of course, it's difficult to get in explicit form of these objects, and but you can compute lots of things from it. Okay, so at least it's integrable in the sense that that explicitly it's. Now, of course, this is the 3 classical ensembles, but then for generalized beta ensemble also people have computed the corresponding functions, Virag and collaborators, and also you can actually obtain the not just the leading order tail, but even corrections to it basically. Okay, and this Tracy-Widom distribution, as I said in the beginning of my talk, that it appeared in many different problems. You will hear many talks in this conference: growth models, directed polymers, sequence matching, and okay, this is not an exhaustive list of people here, but I just put some whichever names came to my mind. And you have heard Johansson's talks here, and then you will hear also Sher and Tomohiro Sasamoto and many other people. Okay, so basically, this is Tracy-Widom has actually appeared in many different problems in statistical physics, and that is why there's a lot of interest in this problem, because and they are also experimentally determined. I mean, in fact, there's an experiment by Sano and Takeuchi on growth models, KPZ equation, and so on, which are also related to this. Those of you who know what is Kardashev-Parisi-Zhang equation, but I'll not go too much into the details of it. Okay, so let's come back to it. So what does Tracy-Widom tell us for our original problem? Okay, so as I said, the Tracy-Widom describes the typical fluctuations. How does the typical fluctuations? What's the probability distribution of that? Okay, and that is given by this function. So this is here. Okay. So this is the typical fluctuation, means that when you are looking at fluctuations lambda max minus √2, when this of order n to the power minus 2/3, small fluctuations. But what we are interested is in large atypical fluctuations. Why? Because I'm interested in this question, right? Pn, which is probability that the lambda max is negative. Okay, what's the probability that lambda max is almost less than or equal to 0, basically? So I'm looking at very this should go to infinity actually. So I'm looking at somewhere there basically at the very large extreme tail here, and so Tracy-Widom, I cannot extend Tracy-Widom all the way up to there. Tracy-Widom is valid only over a small region of n to the power minus 2/3. But I'm interested in very atypically large fluctuations, because lambda max less than equal to 0, that means difference from its average value is √2, so it's of order 1, which is much bigger than this n to the power minus 2/3. Okay? So I'm looking at atypically large fluctuations, and so Tracy-Widom cannot tell me that what is the tail behavior on the left side, but you can also ask about the right side tails. So these are the large deviation tails, that is, which are for finite but large n, where you go beyond the limiting distribution at the extreme tail, where it's not described by the limiting distribution, and you want to know how those, in order to answer my original question, I need to know how these tails behave. Okay? So that is the sort of main thing. Okay, so those of you who are not familiar with large deviation tails, so basically, okay, so let me again go back to a very trivial example. So imagine that you have again m, let's say you have you have some coin and you toss it n times, and let's say m is number of heads. Okay, so then you know that if you ask what's the probability distribution of the m, number of heads, okay, all of you know it's a binomial distribution, n choose m to the power minus m, where m goes from 0 to n. So this binomial distribution, you can compute the mean, it's n by 2, and the variance is n by 4. Okay, so so then you would say, okay, it's a Gaussian distribution, and typical fluctuations therefore are of order square root of n. Okay, and these typical fluctuations are very well described by the Gaussian form. Binomial distribution is almost like a Gaussian near its peak, essentially. Okay. However, if you are interested, for example, if I ask you what is the probability that there are 0 heads, you know the answer explicitly, it's 2 to the power minus n. But if you put in this formula m equal to 0, you won't get 2 to the power minus n, you will get exponential minus n over 2, which is not the same. Okay. So that means the Gaussian approximation cannot describe the the tail behavior, extreme tails at the two sides. Okay. So this is the tail of tails. So basically, if you are interested in atypically large fluctuations, so for example m equal to 0, which means fluctuations of order n in this example, they are not described by the Gaussian form, and you can actually compute this particular example is trivial, because you can actually set m by n to be x, and then take large n limit using Stirling's formula. It's a very nice exercise for people who are not familiar with large deviation function. So then you find that if I set m equal to n, so my fluctuations can be of order n, so I set the thing to be n, and then I ask how does it behave? How does it behave? You just substitute your Stirling formula in this and compute this, and you find that it goes like exponential minus n times some function. This is called the rate function or large deviation function, and this trivial example you can actually compute it explicitly. It's just x log x plus 1 minus x log 1 minus x plus log 2. Okay? So this is called the large deviation function. And in this form, if you now put, so this is valid for all x, okay, all the way, not just near the peak. And in fact, so this function, so if I plot the log of Pn divided by n minus and take limit n goes to infinity, so this is this function, large deviation function, phi of x versus x. So it looks like this, with a minimum here, where it is Gaussian essentially. Okay, and this function, you can actually put x equal to 0 if you want. If you put x equal to 0, you find that log 2, which is the correct result, 2 to the power minus n. Okay? Exponential minus log 2n is 2 to the power minus n. Okay? So you need to calculate the large deviation function. And this large deviation function in this particular example, if you are near the mean, which is half here, so here it actually you recover, because if you take this function and expand around x equal to half, you just get back the Gaussian. So it's a Gaussian peak, but it's no longer Gaussian when you go away from the center around towards the peak. Okay, so this is the basic, essentially this is the main feature of large deviation function with this simple example. So what happens now in random matrix theory? You go from trivial example to another. We have seen the analog of Gaussian distribution there is the Tracy-Widom distribution, but so we have to describe the left and right tail. In this trivial example, there is only one large deviation function which describes both sides, is symmetric function, okay, smooth symmetric function. But what happens in the random matrix case is, let me just summarize the results, because I don't know if I'll get the time to get into the details of the calculations. So basically, what happens is that, so you have the Tracy-Widom, which is the blue curve here, and I have the red and the green, which are the large deviation tails. So when w minus root 2, the fluctuations of order n to the power minus 2/3, that's the typical fluctuations, they are described by this Tracy-Widom scaling function, as I told you before. If this root 2 minus w, that is the fluctuation deviation from root 2, is of order 1, that means if you are probing this tail here, then it turns out that it goes like exponential minus beta n square times some kind of rate function, okay, which I'll show you in a minute. On the other hand, if you are on the right side, that is w minus root 2 is of order 1 here, the green path here, it's actually described by a different large deviation function, also with a different power of n. Okay, so it's n square here and n. There's a very nice physical reason why it's n square and why it's n on the left and right. I'll explain to you in a minute. And you can actually compute this scaling function explicitly. So look at the difference from the trivial example. Trivial example, you had always a e to the power minus n times this function, which is a smooth function. But here, you have a different behavior across the two sides, basically. One side is n square, one side n. And this asymmetry is also there in the tail of the Tracy-Widom distribution. We'll see that. And this is what actually the reason for the phase transition that I'll talk about. Okay. So these functions phi minus w and phi plus w, you can actually compute it explicitly using Coulomb gas and saddle point method, which if I get time I'll talk about it. And so let me just tell you the result essentially. So essentially, I mean this is the explicit form of this function. Don't bother about the formula basically here, but you can actually compute it explicitly, and this is valid for all w less than root 2 to the left of the so remember this curve I was drawing. So this is root 2, and I'm looking at this left part here, and so this is the result, and on the other, and in particular, what you notice is that as w approaches root 2, okay, then this function here actually goes to 0 as a third power root 2 minus w to the power cube. Okay, so and similarly, you can work out the right large deviation function for w bigger than root 2. And it has also an explicit form, but the physics is very different, as we'll see. And it turns out that the same result was derived in a different context by Benarous, Dembo, and Guionnet in 2001, and then later we derived it. They derived it only for beta equal to 1, that is Gaussian orthogonal ensemble. Anyway, these are details. So basically, essentially, you can compute the large deviation functions explicitly. Okay, that's the main thing. And okay, so what is the essential method? I won't go into the too much details of these methods, but basically, idea is essentially simple. So what you want to compute is what's the probability that lambda max, the largest eigenvalue, is less than or equal to some w, right? If you know this, then if you put w equal to 0, you can get back our original question of Pn, probability that all the eigenvalues are negative. But let's say I want to look at general w. So what is this object here? Okay, so I mean I know the joint distribution explicitly. So essentially you have to just integrate. You have a multiple integral going from minus infinity to w. Okay, and so you can write down this probability as a ratio of two partition functions. So this is just the denominator, it's just a constant when w is infinity. That's just a normalization, because when w goes to infinity, this should go to 1. So essentially what you have is a Coulomb gas in presence of a wall. So the denominator is just a free Coulomb gas. So this guy, you know, if you do a saddle point calculation, the density that maximizes this integral here is just the Wigner semicircular law. But what you have up there is that there is a wall, because your lambdas, the particles cannot exceed this wall. So there is a fixed wall at w, and you say that okay, I mean I put a wall, hard wall. So now my guys are, you know, the charges are constrained to be left of the wall, and so as a result, the density that maximizes this integral is going to be different. Okay, and the difference in free energy is or energy, if you like, is exactly what this lambda max is, okay, in the large n limit. So basically, okay, so I'll go very rapidly, this is just the details. Essentially, you have heard it many times. So this is the original method of Dyson, where you basically have a discrete integral, and you can replace it in the continuum limit when n is large by a functional integral. So this is the interaction term. Fx is just the density, new density in presence of w. I want to know how much the density gets modified from the Wigner semicircular law when w is not infinity. Okay, and this is the external potential, and so you have to write down the functional integral here. So this is the energy, and you have to put a saddle point to make the constraint that this integral is 1, and then essentially you have to take the saddle point equation, because the n is large, so you can do a saddle point calculation of this, and you minimize with respect to the function, and you get the fwx, and you substitute back in the action here. That will give you this znw, this partition function here. Okay. So the only difference from the Wigner semicircle and all these things is that you have now a finite wall at w. Okay. So let's see what will happen physically. So basically, if W is very large, much bigger than root 2, I told you when W is infinity, the solution must be Wigner semicircle. So if W is very large, these charges which are happily sitting there, they don't really realize that there is a wall. Okay, so Zn W will be roughly exactly equal to Zn infinity. Okay, so the ratio will be roughly 1, basically the cumulative distribution. Okay, and then as you bring in the wall, as W comes in and it touches the edge, then something will happen there, because beyond that, if you push further, if W is less than root 2, what you see is that this is no longer stable, basically, this Wigner semicircle law. So it becomes unstable, and now you have a new saddle point. The charges all get reorganized. You are pushing your Coulomb gas charge by a wall, so they have to reorganize all of them and find a new optimal density. And so this is the object. So this is, if you can find this new optimal density, that's why I call the pushed gas when W is less than root 2. And so you just need to find out this density, and that is just the cost in energy in pushing this Coulomb gas. And you can see why this is of order n square, because it leads to reorganization of the Coulomb energy of n charges. So obviously energy cost is going to be of order n square. Okay, and so this W equal to root 2 turns out to be critical point. Okay, and because this is where this guy gets pushed. Okay, so you can solve it. I won't go through. I'll go through the details. This is basically essentially, again, you have an integral equation which, but now it's going from minus infinity to W, and as you have heard that you can actually solve this problem by various methods, and you can find the explicit solution. Let me skip the details. Okay, so what you find, this is the main result. Okay, so what you find is that the density, the modified density, when I push this Coulomb gas, okay, so it gets modified from the Wigner semicircular law. And what is the form of this function? So the function looks like this. An explicit form of this function is given by this function here, where L1W is something like that, and basically the support is now from minus L1W to W. All the charges are concentrated here, and there's a square root divergence. There are a lot of charges near the wall, and they go sit from minus L1W to W, and when W actually goes to root 2, you can check from this formula, when W approaches root 2, it goes back to the Wigner semicircle form. So Wigner semicircular solution gets modified, deformed, when you push W beyond root 2. Okay, so this is the reorganization of charges. Okay, and then once you have that, you just put, so this is the energy cost in pushing this charge from root 2 to W, where W is less than root 2, and it gives you so this is the left large deviation function that I talked about, the energy difference between the two cases, and energy cost in pushing the Coulomb gas. And you can explicitly compute, just put this solution back in the action and compute this function. And it's exactly this form. W is less than root 2, it has a non-trivial form, and for W bigger than root 2, it is 0. And notice that our original problem was, what's the probability that lambda max is less than 0? All the eigenvalues are negative. So you just have to put W equal to 0 here. So phi minus of 0, if you put in this function, you get the result that I announced, which is 1/4 times log 3. Okay. Yes. Yes. I'll come to that. Just 1 minute. So basically, so what you see is that this function, if you now, so it's 0. Okay. So how does it look like? So suppose I'm plotting this. This log of this P of Wn, okay, probability that this is the cumulative distribution of lambda max by n square, and taking the limit n goes to infinity. So this is the phi minus of W. Okay, and how does it look like? So let's say this is root 2. So phi minus of W looks like, it comes down here and it goes to 0, it vanishes here as a cubic power. Okay? So this is the cubic power here. And then beyond this, it sticks to 0. So this is the difference from this problem here, trivial problem, where it was a smooth function everywhere, and it was a quadratic singularity here, and then it was a symmetric function here. Okay? There is no phase transition. But here, it actually vanishes as a cubic power, and then it sticks to the origin. Okay? So this is actually a non-analytic point, and this point is what I call the third order phase transition. Okay. All right. So let me. Okay. So and what is nice is that once you have this explicit form, you can see that, okay, so this is the red curve here, right? That's what we have computed so far. And now I want to see that, if I take the argument W to be very, very close to root 2, I should recover somehow the left tail of the Tracy-Widom distribution. They should smoothly match here. And in fact, it does, because you have this phi minus W, and I know that when W goes to root 2, that is, I'm going very close to this mean value, it goes like with this precise coefficient 6 root 2, okay? So you put it in this formula here, and you reorganize these ends, and what you find is that it goes like exponential minus beta over 24 times the particular Tracy-Widom scaling variable, and you remember the tail of the Tracy-Widom to the left was exponential minus mod x cube, and so you find that it's exactly recovers so it smoothly matches the left tail of the Tracy-Widom. And this is to leading order, but actually we have now computed even the correction terms here with Batsroena and Gaito and Selin Nadal, who was my student, and it actually you can recover all the higher order corrections of Tracy-Widom just by matching the tails, but those are details, let me not go into that. Okay. So this is nice, you can recover the left tail of the Tracy-Widom, and yeah, that's what I meant, and as x goes to minus infinity. So this red curve matches smoothly with the blue here. How about the right large deviation function? So here it's a very different physics. So as I told you that when W approaches the root 2, the saddle point actually sticks to the Wigner semicircular law. So if you calculate the cumulative distribution, it's actually 1 for every W bigger than root 2 as n goes to infinity to leading order. Okay? So you cannot really use the saddle point calculation there. So what can you do? So you need a different method. So what you can do is you can actually probe directly not just the cumulative distribution but just the probability density itself, okay, for W bigger than root 2. But physically what is happening is the following. So you ask, okay, I'm looking for configurations where W is much bigger than root 2. W is the largest eigenvalue. Okay? So what are the configurations which are going to dominate my integral, my partition function? So the configurations that dominate, it turns out, are when one of this lambda max is much bigger than all the other guys basically. Okay, so here is all the rest of the n minus 1 charges sit in the Wigner semicircle. They don't get modified. You just pull one charge from the C, and that is the reason why, in fact, this energy is of order n. Because so you ask, what's the probability that lambda max is W? Some W. So it's just the energy cost in pulling this charge from the Wigner semicircle. So it's actually a much simpler calculation, and that's why it's of order n, because you're just pulling one charge, so the net change of energy is of order n, because the interaction of this charge with the rest of the Coulomb charges. Okay, so the rest of the charge doesn't change from Wigner semicircular law. So essentially you just have to do one integral and plus the change in the external confining potential due to this. So you can actually compute this very trivially, and you get this exact large deviation function very simply to leading order. And okay, now there are results for subleading orders and so on, but let me not go into the details. So and again, from this large deviation function, what you see that as W goes to root 2, it vanishes like power 3/2 with this coefficient. And again, if you put it here and reorganize, you recover exactly the right tail of the Tracy-Widom distribution. Okay, and this is sort of one way to compute the tail of the Tracy-Widom distribution without calculating the actual Tracy-Widom calculations, which involves complicated Fredholm determinant and more technical stuff. So this is actually a very simple physical method to compute these guys. Okay, so here is some numerical simulation. So what you see here, what I'm plotting here is the minus of the log of the probability distribution, PDF of the lambda max, and here is just the scaled value. And what you see, the red curve here is the Tracy-Widom. So Tracy-Widom is very good near the mean, as I said, but these circles here are the numerical simulation points. What you see is that when you go away from this peak, you find that Tracy-Widom is no longer good to describe this. You need the large deviation form. The blue is the left large deviation function, and the green is the right large deviation function, and they work very well. Okay, fine. So let me just summarize this for you for the moment. Is that so? Essentially, I mean, this is the main picture I want you to remember. That there is a PDF here, and the limiting distribution. Typical fluctuations are described by the so-called Tracy-Widom distribution, which is sort of well known and well established. And but there are large deviation tails which are not captured by Tracy-Widom distribution. So for this, you have to actually compute them, and you can actually compute them explicitly. And there are different physics here. One goes like n squared because you're pushing charges, and the other goes like n because you're pulling charges. Okay. So this is this statement then. So cumulative distribution, if I look at this, is same thing as I said. For W less than root 2, W is the largest eigenvalue. So it goes like e to the power minus beta n square, and when w is bigger than root 2, this is the PDF. So if I integrate, the cumulative distribution goes like 1 minus some constant times this. Okay. So as I said, if you take the log of this, so this has the interpretation of free energy essentially. It's a partition function, so log of this is the free energy, and the n square is the correct scale. And if you take the n square limit, so this is in some sense the free energy per degree of freedom. So this goes like 5 minus w, and it goes like cubic power here as w goes to root 2 from the left side, and it's 0 because here it's a non-perturbative correction. It's exponential minus beta n. So if you take the log of this and divide by n square, it's exponentially small, so it's 0 in the n going to infinity limit. So strictly in the n going to infinity limit, you have exactly this function here. So there is a non-analytic point where the third derivative is discontinuous, and this is the third derivative. Okay, so and so essentially for finite n, you have a crossover between this left branch and the right branch, and the crossover function is precisely what the Tracy-Widom function. And those of you who know about the gauge theory, this is what is called the double scaling limit in the large n gauge theory. Okay, so here is a phase diagram. So this phase transition I was talking about. So this is the same object I'm plotting minus this is just a free energy basically per particle. As a function of this w. So in the limit when n is very large, infinite, you have strictly a third order phase transition. This is a non-analytic point. For finite n, you have this guy pushed gas here, I call it pushed phase, and you have this unpushed or pulled phase, okay, and they are connected by a this blue dot here, which is precisely the Tracy-Widom function. So Tracy-Widom is just a finite size crossover function from one phase to another phase. Okay, and so if you plot the phase diagram like this. So if this is my w and this is root 2 here, so this is the critical point here. So if I'm to the left of critical point, then I'm pushing my charges. Okay, so this is the pushed gas, and if I'm to the right, it's the unpushed gas, and there is a crossover. Strictly in the n going to infinity limit, you have a strict phase transition. As for infinite, there will be a crossover from pushed to unpushed phase. Now this phase diagram, as I said, those of you who know gauge theory, I'm not. Maybe I'll elaborate more detail in my tomorrow's lecture. But basically, this is exactly the same phase diagram. It's a sort of identical phase diagram that you find in the 2D Young-Mills theory in the large n limit. So I don't have time to explain to you 2D Young-Mills theory, but basically you can think of the 2D Young-Mills theory as a theory on a lattice where think of Ising model. So Ising model is just a spins which are interacting with each other. But Young-Mills theory is basically not spin, but there is a unitary matrix n by n which is sitting on each lattice link. And they are coupling, they are interacting with each other in some way, and there is an interaction constant which is called the coupling constant. And if you plot the 1 over g, the coupling constant, versus 1 over n, then in the n going to infinity limit, you have a phase transition from what is called the strong coupling phase to the weak coupling phase of the gauge theory. So this is like the QCD strong coupling phase and weak coupling phase. And of course, for finite n, there is a crossover between them, and there is a double scaling regime, and this is the exact analog of this Tracy-Widom crossover function here. Okay? So now this is of course just a same universality class. There is no one-to-one correspondence between the two, except there is an indirect connection which I'll talk about tomorrow. Indirect connection between the what is called the Coulomb problem and this precisely this Gross-Witten-Warria lattice gauge theory, and there you can see that exactly the same integral, same partition function which appears in the two problems. Okay? But basically, the point is this is the main message, that the left large deviation tail of lambda max, the pushed gas, corresponds to the strong phase of Young-Mills theory, and the right large deviation corresponds to the weak phase of Young-Mills theory. Okay, and precisely the Tracy-Widom is just a crossover function in the double scaling regime where w goes to root 2 and n to the power 2/3. The same n to the power 2/3 appears here, so it's in the same universality class. Okay, and in fact, this Spanlevy equation that I talked about was actually originally found by Periwal and Sevis in 1990, just exactly around this critical point. Okay, of course, they didn't have any interpretation of a probability distribution of some random variable, and later in the continuum case by Gross and Matitsin, and the same year as Tracy-Widom was found. Okay, so now, so this is the sort of main this thing of my talk. So I'll go to the experiments now, just to wrap up the talk. So. Okay, so I've talked about Gaussian matrices. Now you can actually generalize to Wishart matrices, the matrix that I started with, namely the covariance matrix X dagger X, and you can do the same exercise. So you have a density of states there. Analog of the density of states is Wigner semicircle law. Here it's called the Marchenko-Pastur law. This is the case when this is a rectangular matrix, square matrix n cross n. So Marchenko-Pastul law. And again, you look at the distribution of the largest eigenvalue. So you find the limiting typical fluctuations of order n to the power minus 2/3. And in fact, it was a classic work of Johnson, who is there in the audience, and Johnston, who showed that this is actually a Tracy-Widom. Limiting distribution is again Tracy-Widom even in the Wishart ensemble. Okay? But again, you have a left and right large deviation tails, which you can compute by the essentially same method that works for Gaussian case. And so we computed these functions explicitly, psi minus and psi plus, so they are known. Okay, so here is a formula, but don't bother about the details of this formula. So here I come to this. So basically, Wishart case, again, same third order phase transition happens. It's the same university class as the Gaussian case. And again, you have a third order phase transition. And again, you have this similar type of large deviation functions. Large deviation functions, of course, are not universal. Only near the critical point they get universal. Okay? So this is the recent experiment from the group of Neil Davidson and Wiseman. So what they do is actually they have a coupled fiber laser. So fiber laser means basically what is the system. So I mean, those of you who know optics experiments, so if you have an optical interferometer, so what you have is you have a so you have something called beam splitter, and you have so imagine that you send light from here, and you send light from there. So light means basically electromagnetic wave. Okay, so you have a plane wave essentially, and you say that okay, so I have two such plane waves which are going through this, and there is a mirror here, which is called the beam splitter. Okay, and this light goes there and gets reflected, and part of it gets transmitted and comes back, and this light also goes there, gets reflected, and part of it gets transmitted. So they come back. Go this way, then they come back, gets reflected from this, and then they come back to this, and this guy comes back to there. And so essentially, so if you say that your A1 and A2 are the amplitude of the plane waves that goes from here and here, so A1 e to the power ikx and A2 e to the power ikx, where k is the wavelength, and then they make this trip, what is called the round trip through this optical cavity, and what comes out is A1 prime, A2 prime. And they are related by a matrix which is called the round trip propagation matrix. Okay, so and now you can think, okay, instead of so in case of lasers, instead of just ordinary light, you have laser light, and instead of beam splitter, what is called is a laser coupler, the fiber laser coupler basically. So this is this object here schematically. And so what you have is now you can have two, but you can actually put many of them together, many such optical lasers, and couple them in many different ways. This is one way of coupling them basically, and so they get coupled, and essentially so you have this round trip propagation matrix, which is now n by n matrix, and these matrices are actually random because these lengths, effective lengths of these lasers, all these lasers, they can actually fluctuate with time because of acoustical fluctuations and thermal fluctuations also. And what they do then, finally they look at this this round trip propagation matrix, and you put all of them together, and there's a lens which captures the maximal output, and basically you can measure this output, and this maximal output of power is precisely proportional to the largest eigenvalue of this round trip propagation matrix. And what they have done in a series of papers is to show that this object round trip propagation matrix you can actually write in the X dagger X form. So it actually has a Wishart distribution essentially, and so they can, by measuring the total output power, they can actually measure the distribution of the largest eigenvalue of the Wishart distribution. Okay, and this is what you see. You can't see very well. So they plotted here. So this is the scaled output power, which is just the lambda max in this knowledge, in this language, and this is just the PDF of the lambda max log scale. Okay, so what you find is so these circles here, they are the experimental points. Okay. And this solid curve here this is actually a Tracy-Widom beta equal to 1. So this is solid curve is a Tracy-Widom beta equal to 1. Okay, and you see that it doesn't work very well at the tails. Okay, and these dashed lines here are actually the functions that we predicted. And so if you zoom in this part and scale it, just zoom in that part and scale it differently, you see a beautiful collapse on the Tracy-Widom beta equal to 1. So this is the orthogonal Tracy-Widom beta equal to 1. Okay. So these are the experimental points in the solid curve. And on the other hand, if you if you focus here on the tails, these dashed lines here are the functions that we predicted, large deviation functions, and here also this is the large deviation functions that we predicted. Okay? The left and right are different, and the third order phase transition essentially occurs here. Okay, okay, so so this is the, so I'm just wrapping it up now. So essentially, this same third order phase transition also appears in many other problems. Maybe I'll talk about that in my other lectures. So bipartite entanglement of a random pure state, and then conductance and short noise that Kedar talked about this morning, and also you heard from Carlo Binecker's talk, and also non-intersecting Brownian motions and random matrices. This is also direct relation to 2D Young-Mills gauge theory that Gregory Scher is going to talk about. And so this is many different problems where these techniques of Coulomb gas and this general third order phase transition appears. So my conclusion, the take home message is precisely this, that there is a third order phase transition which is ubiquitous. You find in many different problems. And essential mechanism is that you have a charged droplet with a square root. So remember that Wigner semicircular was like this, and this is the picture that you have a wall. So whenever you have a charged droplet with a square root singularity here, and if you hit with a wall, then you always have a third order phase transition. And if you have that third order phase transition, then close to this critical point, that is when it very close, the wall is very close to this critical point, you always have a underlying Parnleve 2 equations. Okay? So let me just acknowledge my collaboration. So my students were Celine Nadal, who is now at Oxford postdoc, and Julia Randen-Farling. And I had the opportunity to work with many people who are already present in the audience. In particular, Kedar Damle and Arul Lakshminarayan, Gregory Scher, and Pierre Vivot. All four of them are present here. So it was a pleasure to work with them. And okay, so thank you very much for your attention.
Thanks for that nice trip to random matrices. So any questions? You can answer a couple of quick questions.
Perhaps it goes far down that. Well, why is this experiment not a trace of this WW diagram? How would it imagine how?
Yes, no, actually, so no, they I mean, somehow they, I mean, okay, this is very hard to read from their paper, but basically they some, these things operate somehow at the maximal power, which means somehow it's only picks up the largest eigenvalue, not the full trace, essentially. Yeah. Only the, the largest one, which is maximum absorption, basically, and it works in that mode, basically. So. Absolutely. No, that's why the optics experiments are beautiful, actually. You can do anything with optics experiments. So it's, yeah. Yes. Yes, absolutely. I think you are right. It will give rise to it. There's nothing special about logarithmic interactions. Okay. I mean, it's you can have any other interactions, and perhaps it might actually long-range interaction might give rise to in this kind of phase transitions. So it's not ruled out. No, so method that I use, I mean, I didn't have time to go too much into details of the calculations, but basically, there we use this integral equation, which comes from the logarithmic potential, and those integral equations, there's an explicit solution due to trichomy for arbitrary potential. Okay. In fact, I mean, I should emphasize here, this trichomy solution was somehow not that well known in the physics literature in particular. If you look at the original paper of Brezin, Zixen, and Parisi-Zubair, where they were actually they're not computing this problem, but they were looking at the density of states for a potential, which is, external potential is not just quadratic, but there is a, correction term, Gx4. Okay, so quartic potential. So, to solve this problem, they came up with this resolvent method, which is very nice, of course, okay, and it works very well. But resolvent method actually, you have to make a guess at some point, and it works very well for polynomial potentials. But if you have an arbitrary potential, resolvent method is, you have to make a guess. You may be good, you may be lucky to guess, and then a posteriori you can prove that this is a unique solution if you find a solution. Okay. Whereas, I mean, they missed the fact that there was a solution by trichomy already, which was well known from 1951. Okay. There's an explicit solution of trichomy, which says that. So this is an inverse electrostatic problem. So if you have some function g of x, let's say, and you have a principal part let's say some A to B, and rho x prime, dx prime, x minus x prime. Okay. So this is like an inverse electrostatic problem, right? So in electrostatic problem, I give you the charge density and I ask you to calculate the potential. But here it's opposite. Here I know what the potential is. This is just the force balance condition. I know what the potential is, and I want to compute what the charge density is. Okay. So you cannot so easily invert, because this is where technically this is where the one-dimensional versus two-dimensional. If the problem was in two-dimension, then you could take a del square, and then it will be just a just a simple Laplace's equation, the delta function basically, and you can find the density very easily. Okay. But you cannot so easily invert it in the one-dimensional case, because Coulomb logarithmic interaction is not the Coulomb interaction. So you cannot reduce it to a Poisson's equation. However, it turns out that as long as you have a single support, that is your solution is non-zero from A to B, if it is a single support, then there is an explicit solution of inversion, and this is actually very useful because it appears in many different problems, which is if I get it right. So plus some arbitrary constant here. So this is an explicit solution for any smoothly behaving g of x essentially. Okay. It does not have, so for example, you could use this formula for the quartic potential, and you would get the Breza-Isaacson-Parisi solution in one line essentially. Okay. So this is not that well known somehow, this Tricomi solution, and for us it was very useful actually. So this yeah. Yes. No, you have to have a long range interaction, of course, yes, certainly, yes. As you know, in a one dimension, I mean, you cannot have phase transition unless you have a long range interaction.
One last question.
Yeah. Yes. Yes. Sorry. Say it again. Last part. What did you say? Yes. Very rare. So most of the, as I said, most of the stationary points, at least within this random Hessian model, are actually saddle points. Okay. So the actual minima are very rare. If you take a snapshot of all the stationary points in your landscape, you find that the minima are probably only 1% of them are minima, maybe less than 0.1% are minima. No, but in the Gaussian case, where you have a symmetry between lambda max and lambda mean, because it's a completely symmetry, lambda, this probability distribution is invariant under the symmetry lambda going to minus lambda. Okay, so which means lambda mean has exactly the same statistics as lambda max. Okay, so therefore the statistics of the local minimum is exactly same as the statistics of local maximum.
Professor Satya Majumdar will be here for the next few days. In fact, the next two lectures are tomorrow evening at 4 and then on Monday evening at 4. So I'm sure he will go into more details and other directions. So please do come. And so, but now let's thank Satya for his very nice lecture.